Hello and welcome to this video. So today we are going to discuss about the basics of superconductivity, and this will be a very basic video on superconductivity. So I will introduce you to superconductors, what is Meissner effect and what are various types of superconductors. Those things will be discussed, and if you are a BSc Physics student, MSc Physics student, or if you are preparing for IIT JAM, then this particular video will be useful to you. So now let us start. What are superconductors? Okay, so as the name itself suggests, superconductors. I mean, these are conductors, but they are super. So, conductors means conductors of electricity, but they are super. Super means they are of very good quality. So now, when can a conductor be of good quality? When it experiences no resistance, or it can conduct electricity without offering any resistance. So that is a superconductor. Superconductors are material that below a critical temperature lose all electrical resistance. I mean, they can conduct electricity without any resistance and electric current to flow without any energy loss or without any heating of the conductor. So this particular phenomenon was discovered in the year 1911 by a Dutch scientist, Heike Kamerlingh-Onnes, and who was studying mercury's resistance, and the mercury sample was cooled and the resistance of mercury dropped to 0 when he was cooling it at 4.2 Kelvin temperature. Okay, so what is liquid helium? We have already discussed. I will give the link here on the I button. And at liquid helium temperature, I mean, helium is a gas, and when it becomes a liquid at extremely low temperature at 4.2 Kelvin, at the temperature mercury lost all its resistance and it became a superconductor. The phenomenon was first observed by Heike Kamerlingh-Onnes in the year 1911. So this is the particular scientist who first invented superconductivity. Now let us look at this picture. If you look at this picture, things will be more clear to you. So here this plot is about temperature and resistance. Okay, temperature in Kelvin scale and resistance in ohm. So for a normal metal, if you keep decreasing the temperature, its resistance will also decrease, but it will never be 0. It will be very close to 0 at very low temperatures. Okay, or in other words, if you increase the temperature, the resistance of a metal increases. We all know that. But what about superconductors? Superconductors, the resistance will keep on decreasing like this, and at a particular temperature, which is also known as Tc, or the critical temperature, the resistance of the superconductor will drop to 0. So this green line, it drops to 0 here. Okay, electrical resistance of a superconductor drops to 0 at critical temperature. So this is the difference between a normal metal and a superconductor. If you cool down both, the superconductor will have a 0 resistance at a critical temperature, and this is what Heike Kamerlingh-Onnes observed when he was cooling down mercury, and he observed that at 4.2 Kelvin temperature, the resistance of mercury dropped to 0. Okay, so some key properties of superconductor are 0 electrical resistance, no power loss, expulsion of magnetic field or Meissner effect, which we will discuss right now, then critical temperature or below the temperature below which superconductivity occurs. So again, let me show you this picture. This is the Tc critical temperature. At this temperature or below this temperature, superconductivity can be observed. Okay, now what is Meissner effect? That is what we are going to learn. So Meissner effect is nothing but complete expulsion of magnetic fields from the interior of a superconductor when it transitions into the superconducting state below critical temperature. Okay, so when the material becomes a superconductor, it has got the ability to expel all the magnetic flux lines from its interior below critical temperature. Okay, I will show you the figure, then it will be more clear to you. So look at this picture. So here this blue sphere, it is a normal metal, and at temperature above the critical temperature, so magnetic field lines, they can enter through the metallic sample, and at a temperature below the critical temperature, this magnetic field lines have been expelled from the interior of the metal, and this is what a superconductor is. Superconductor, remember, below critical temperature we can observe superconductivity, and superconductivity refers to the expulsion of a magnetic field, and this is basically Meissner's effect. Now, explanation: in a normal conductor cooled below certain temperature, magnetic fields can stay frozen in. Okay, magnetic fields will pass through the sample. In contrast, a superconductor actively expels magnetic fields from its interior. This is called Meissner's effect. Okay, this leads to magnetic levitation. A magnet that can float above a superconductor because of this expulsion. Okay, magnetic levitation. What is magnetic levitation? Let me go back to this thumbnail. So this is a superconductor and this is a magnet. So you can see this particular superconducting material is not touching the magnet, so it is above the magnet, and this is due to the phenomenon of magnetic levitation, which is as a result of Meissner's effect. That means, what do we mean from all this, what we have learned right now? That superconductors are repelled by a magnetic field, or superconductors magnetize in a direction opposite to that of the magnetic field. Okay, so let us understand it from here. So B magnetic field vector is 0. That means superconductor, inside a superconductor, magnetic fields lines are expelled. Okay, then B vector can be written as mu naught m vector plus H vector. M vector is the magnetization vector, H vector is the magnetic field intensity vector, therefore which is equal to 0, but mu naught permeability cannot be 0, so M vector equal to minus H vector. So susceptibility is M vector. Okay, susceptibility, we know magnetic susceptibility is the ratio of magnetization to the magnetic field intensity, and in this particular case the susceptibility is equal to -1. That means what? Magnetic susceptibility 1 means -1 means what? That superconductors are perfectly diamagnetic materials. Okay, why diamagnetic? Again, let me show you this particular figure of Meissner's effect. Superconductor magnetic field lines are expelled from the interior of a superconductor, and that is why superconductors behave as perfectly diamagnetic. Now, why this happened? Lenz's law of electromagnetic induction, you must have learned about this, so we can also refer to Lenz's law of electromagnetic induction, which I will not explain here, but you can refer to that particular law. Okay, so we have learned that superconductors are perfectly diamagnetic. Now, superconductors are broadly divided into two types, okay, based on how they interact with magnetic fields. So what are type 1 superconductors? Okay, superconductors are of two types, type 1 and type 2, and that is based on how they interact with magnetic fields. Type 1 superconductors, pure elemental metals like mercury, lead, etc., they exhibit complete Meissner effect up to a critical magnetic field Hc. Above Hc, superconductivity is destroyed, and they are less useful for practical applications because of low critical field and low critical temperature. Okay, so these things, okay, let us understand from this figure. So this is the magnetization curve of a type 1 superconductor. Along the x-axis we have magnetic field intensity, along y-axis we have magnetization. Magnetization is -m, because we know that for superconductors they get magnetized in a direction opposite to that of magnetic field. So if you keep on increasing the magnetic field intensity, then magnetization also increases, but in an opposite direction. So that is why susceptibility is -1, that we have already learned. And then as soon as it reaches the critical magnetic field, the susceptibility drops to 0, and above this critical magnetic field the superconductor becomes a normal metal. Okay, normal state. So from 0 to Hc it is in superconducting state, and above Hc it is in normal state. Okay, so that is why it, what is written, exhibits complete Meissner effect. Okay, up to Meissner effect means what? Up to Hc, up to the critical magnetic field, Meissner effect is observed, means what? Magnetic field lines are expelled from the interior of a superconductor. That is why the magnetization and magnetic field intensity curve is a straight line up to the critical field. Okay, once again I suggest you to pause the video and look at this particular plot very well, and for that I am again going back to this particular figure. Okay, so this is type 1 superconductor. This critical magnetic field is generally very low. And what are type 2 superconductors? Generally alloys or complex compounds like niobium, titanium, YbCO. These are like type 2 superconductors. They have higher critical temperature also as compared to type 1 superconductors, and they generally have two critical fields, okay, Hc1 and Hc2. I will show you in the magnetization figure. And between Hc1 and Hc2, magnetic field partially penetrates the superconducting sample, and we get kind of a vortex state, or which is also called a mixed states, okay, which can carry higher current densities even when strong magnetic fields are applied. Okay, they are widely used like in MRI machines, maglev trains, and particle accelerators. So type 2 superconductors are in fact more useful than type 1 superconductors, because type 2 superconductors can be used in a number of applications. Okay, so this is the magnetization curve, magnetic field along x-axis, magnetization along y-axis. So see, up to Hc1 magnetization increases, then above Hc1 magnetization begins to drop, okay, up to Hc2, and above Hc2 the magnetization completely vanishes. And here if you keep on like if you so how is the magnetization actually? So here it will keep on increase and then it will begin to decrease, okay, it will begin to decrease like this. So up to so we can consider another critical field between Hc1 and Hc2, up to which it may behave like a type 1 superconductor. But here what is the thing, between Hc1 and Hc2, this is a mixed state. Mixed state means mixed normal state and a mixture of normal state and a superconducting state, okay. The superconducting state exists only up to Hc1, and between Hc1, okay, remember once again, for a type 2 superconductor, the superconducting state exists only up to Hc1. Between Hc1 and Hc2, it is the mixed state, like both superconducting and normal states coexist here, and above Hc2 it becomes a normal state. That means the magnetization becomes completely zero, or the material is no more superconducting. So unlike type 1 superconductor, in case of type 2 superconductors, we have two particular critical magnetic fields, and that is why we can use, it is very easier to use type 2 superconductors for practical purposes than type 1 superconductors. So the difference between type 1 and type 2 superconductors have been tabulated, okay. Material pure elements, type 1 or type 2 alloys or compounds, critical field only one BC or HC, and here we have two critical fields, BC1 or BC2, or simply HC1 and HC2. Meissner's effect is complete, okay, but here in type 2 superconductor it is mixed. So magnetic tolerance is low, and in case of type 2 superconductor it's high. Applications of type 1 superconductors are limited because of low critical temperature and low critical magnetic field, but in case of type 2 superconductors, they have broad application potentials or applications due to higher critical temperature and higher critical magnetic fields, okay. So these are the main differences between type 1 and type 2 superconductors. Very easy, it's easy and also important, okay. Almost no less asked in examinations, type 2 superconductor magnetization plot, and here we have type 1 superconducting magnetization plots, and here are their differences. So friends, this was all about today's discussion. We have discussed about the basics of superconductivity, Meissner effect, and types of superconductors. I hope you have liked this video, and if you have liked it, please like, share and subscribe to this channel, and I hope to see you soon in another such informative, interesting video. Thank you very much.